Welcome back, everybody. Today's video is talking about implicit differentiation and higher order derivatives. Now, higher order derivatives is a fairly straightforward topic, so I'm just going to cover that briefly and focus primarily on implicit differentiation, which is a bit more complicated. All right, so higher order derivatives. I talked about it in class a little bit, but it's possible to take derivatives beyond the first. To do it, well, to take the second derivative, you just take the derivative of your original function and then take the derivative of your derivative. And if you want to go third, only take the derivative of your second derivative, and so on and so forth. So you always have to find the derivative of the previous function. So I'll show you a little bit of notation that goes along with it. So for the prime notation that we've been using, we have for second order f prime, double prime, for third order f triple prime, but using that for a lot of derivatives can get really ugly. So if we end up going beyond 3, we will use parentheses and put the number of the derivative in it. Now, you can use this for first, second, and third derivative if you so choose. It's just not the standard notation. The other way you can do this is using the df/dx notation, where you will see for the first order, it's the derivative of f with respect to x. Second order, well, it's the second derivative of f with respect to x both times, and so on and so forth. So this is the more standard type of notation that you will see out there. It's a little longer to write, but it has uses over the standard prime notation. Now, one last thing I want to talk about for higher order derivatives is if you have the position function of an object, you should all know that taking the first derivative will give you the velocity function. But then if you take the derivative of that, it will lead you to the acceleration function of the object. So that's one of the reasons why higher order derivatives are useful. You can go beyond that. There's like jerk and a bunch of other funky stuff that, unless you are dealing with physics, most people don't care about. All right. Implicit differentiation. This is a bit more complicated, but it's a really useful tool. So up till this point, whenever we've done the derivative, it has been in standard function notation, which pretty straightforward to deal with. But if it is not in function notation, you're going to have to use implicit differentiation. Now, what do I mean by not in function notation? That means the y is intermingled with everything else in the function, and it's all messed up. Or it's impossible to solve it for an individual y, in which case it might not actually be a function, but you can still take the derivative of it. Now, to do this, you need to take the derivative of each part of your equation separately with respect to each variable you're dealing with. I'm going to go through an entire example with you for this, and then I'll let you see the exercise to work on it. Now, whenever you do this, to keep things straight, you need to multiply each part by what variable it was taking the derivative with respect. I'll get more into that in a moment. And then you're going to solve for dy over dx. So this is going to end up showing you your final function. So let's take a look at an example. So we have this function, 2x squared plus xy plus y squared equals 2. Now, slight issue, this is not actually a function because it would not pass the vertical line test. So to take the derivative of this, we have to take the derivative with each part. Let's start with x and treat y as a constant. So the derivative of 2x squared will be 4x. The derivative of x times y will just be y, because y would just be classified as a constant. Derivative of y squared, well, that's just going to be 0, because y is a constant, so y squared would be a constant when we talk about x. And the derivative of 2 is 0. So we get this part here. Now, I said before that you multiply it by with what you would taking the derivative with respect to. If you're taking the derivative with respect to x, you do multiply it by dx. So that'll give you this function, or this notation here. Now you do the same thing, but you're doing it with y. And when you do that, you'll get this derivative, and you'll have dy attached to each of these. Now, those are two separate equations, yes, but then for each part separately, what we need to do is add these equations together, which will give us this. So you can see where this part was taken with derivative with respect to x, respect to x, respect to y, respect to y. Now, after this, we need to solve for dy over dx. So if you move everything with a dy to one side of the equation and everything with a dx to the other side, there should be no terms without at least one of these. All right. Then you can factor out the dx and factor out the dy, which when you have that done, you want to divide by dx and divide by whatever's in front of the dy. And that is your derivative. All right. And that is the implicit differentiation. Now, the reason why it is called implicit is because you have to know what x and y are to really deal with anything. You can't just put x in. It's not set up in such a terms of only defined by x giving you y. It's a bit more ugly than that. All right, so for the exercise, I want you to find the derivative of the natural log of x plus y minus x equals to 3x squared. So I want you to find the derivative of this entire equation. All right, so go ahead and pause it and try it out. All right, if you're stuck, you need to find the derivative with respect to x, which is this part here. All right, now you should be able to figure out what the next step is. If you're still stuck, or you've already completed it, you should get something similar for derivative with respect to y. Keep in mind, x is constant, so the derivative of that would be 0 when we talk about the y's. All right, so go ahead and continue from there. Now, hopefully you've determined what to do next. If not, you need to add the two functions together. And keep in mind, positioning, those do matter. All right, go ahead and finish that up. And if you have already or are stuck, you now need to solve for dy dx, which I skipped a couple of steps, but you should have your final equation over here. All right. Hopefully you learned something, and I will see you in class.